16.4 is on what's called Green's theorem. So this is getting into the theorems that basically convert back and forth between double integrals and triple integral, well, single integrals like a line integral, and area like and a double, versus maybe surface area and volume. So it allows us to kind of go back and forth between how to calculate something, and in a lot of ways it's easier to do one way than the other. That's that concept. And it has vector fields all built in. So there's vector fields, doesn't work without that essentially. So let's go through the definitions and examples here. So a curve C is given by x of t, y of t, and it's simple, meaning it doesn't cross itself. Okay, so here's a few of my examples. So simple, not closed. This is simple and closed, and this is closed but not simple. Okay, so simple closed curve is usually what we are going to define things on. You can define it more like this, down below I just drew, but it's a little more difficult. You just do it separately, essentially. Okay, a plane curve is simply connected if its boundary consists of one simple closed curve. So simply connected is the case that we want to see. So it's the, generic, easy one to look at case. So here's Green's theorem. So let R, our region, and these would be regions. Maybe I'll label those. Oh, I did label them, never mind. Okay, so let R be simply connected with a piecewise smooth boundary C, oriented counterclockwise. So I want us to go counterclockwise like I just drew. M and N have continuous first partials in an open region R. Then the line integral m dx in dy is equal to the double integral over the region. So it's like you're integrating over the entire region. And then you just subtract the partials of n and m. So makes things rather nice to calculate. Do have in mind, though, that we have a vector field acting on the part, whatever it is. So you have a vector field going through here. That's the m and n part. And then this is the curve. So this is what you're integrating over. So it's like, do you want to do a line integral and integrate this way? This would be a line integral. Or you can do a double integral and do the partials. Now, a lot of cases, that's going to be easier. Here's look at this example. I'll leave up the theorem so you can see the theorem for a little bit. All right, so the curve is given later. 4e to the root x dx sine y plus 3x to the squared dy. So here's m and n. So the line integral would look like this. Okay, and c, that normally would say that. C is given by this arc. It's an arced region, so that's given. So C is the boundary, the one in yellow there. So M and N have continuous first partials. R is simply connected with a piecewise smooth curve. So that's what you have to establish. This and this are the hypothesis of Green's theorem. So here's my conclusion here. Therefore, we may apply Green's theorem. So to apply Green's theorem, we just look at those partials, partial in x, partial in y, and you're evaluating over the region R. Okay, so if you're evaluating over this region, you got to choose how to evaluate that. And if you do it in polar, then you can, it's a bit easier. Okay, so finish that one out. And you'll get 2b cubed minus 3a cubed. 2b cubed minus a cubed, sorry. All right, evaluate Next question. We'll just try this one. This is same. This one's pretty easy. Look this one up. So here's your curve. Let me zoom in on that. So here, this is given. So here's your curve like this, in that direction. So the region would be everything inside. So this is a simple closed curve. It's simply connected. That's the term they use. So you have to establish the hypothesis, and then you can apply Green's theorem. In this case, when you do those partials, you get 0. So what would that tell you about the vector field then? Well, if these partials, the difference is 0, then the vector field in question is conservative. Okay, so that's related. Okay, so that's Green's theorem. Pretty straightforward theorem. Okay, good question. 16.5 is on parametric surfaces. So this is a little more involved. So first, recall curves defined parametrically. We've already seen that for just a single variable. So R of t, we've seen this. And then this is the 3D case, right? So you get like a helix or something, or any sort of curve in space. So to define a surface parametrically, we need 2 more variables. So it's like you need one variable to make it move along the x-axis, and another variable to do it along the z-axis simultaneously, because otherwise you just get this. We want to talk about a curve that gives us the entire surface, like that. All right, so we need 2 variables. So we pick 2 variables that are real, and we call that a region D. So 2 points in D are transformed to a region in space. So you have D basically is mapped to a surface in the x, y, z coordinate system. So that's your mapping. A region, and then you get a surface. So here's an example of what it would look like. So R of uv. So you have x, y, and z all are functions of 2 variables. So take some time to think about how that would change what something would look like. So let's take a look at this next example. This we did earlier with this v being the same variable u. We called it t. So when we first talked about it, we had u as a t, the same variable, t, t, and t. So what that gives you is basically the helix. Okay, because that's the circle, radius 2. But now v is another independent variable. So because it's independent, then you get all of these values at every stage as well. So you get the cylinder. So it's just the sides of the cylinder that go on forever, basically, is what you're getting. So you can eliminate the parameter, and you get this, but the z value, which is here, is arbitrary. Okay, so ponder how that works, why you get a surface. Okay, let's do rectangular to parametric. Okay, so take a look at all that. Basically, all you got to say is x, y, and f of x, y. It's actually kind of nice to go back and forth, although to solve for things, sometimes you get roots and stuff. So write in parametric form the top half of a sphere. So here's a sphere. When you solve for z and take the positive root, you get just the top half. So that's, where is it? That's this. So we take just the positive half. And then in parametric, you just say x, y, in that function. So that's pretty straightforward, although you can see it gets messy real quick. All right, so next question, take a look at this one. Vector valued function whose graph is defined by x squared plus 4y squared. Okay, so that's an ellipse. And then this, this isn't something I would expect you to know right off the top of your head, but you can make an ellipse just like we did the circle with cosine and sine. And then you have the major axis and minor axis. So the major is the 4, minor is the 2. Okay, and then this one, we notice this little, they snuck that in there. Z is arbitrary. So that means Z is just another independent variable. So that has to be, there's your Z that's arbitrary. It's independent of your U and V. So you get the ellipsoid, or ellipse actually, but it's a cylinder, so it goes straight up like that. Okay. 16.6 is on surface integrals. So this is taking the concept of parametric surfaces and then adding a function in there. Okay, so let f of x, y, z be a function. S is a surface defined by z of x, y, or r of u, v. So here's what we were working with before. This is what we just defined as a surface. So a surface integral is integrating over the surface. Instead of integrating over a region in a plane, you're integrating over the surface. So you're taking these little patches. This is, I don't have time to spend on this today, but you're taking those little patches, you do the cross product and you get the area of that little patch. Then you add up all those little patches. And you can kind of see I drew it here where it doesn't quite touch the surface. It's just it's a flat little thing there. But as you shrink, of course, the partition, as you get the partition smaller, the patches are insignificantly off that surface. So that's the idea. So if there's no function here in the integrand, then you're going to get area, right? Then you get area of the surface, or surface area, because you're just adding up those patches. Okay, so this is the derivation of that. I think it's the whole thing there. Yeah, so you can go through the derivation. Not going to spend a lot of time on that. It's a lot there. Okay. Right, so let's see. Yeah, this takes some work. So I wasn't. So again, I won't go through it in the video. So look at how that's done, and check it out. Okay, let's look at this example. Evaluate the double integral over the surface S of f of x, y, z ds. So they have to give you f of x, y, z and the surface. Okay, so the surface is defined by the upper half of this cone. Okay, so there's your surface. And above this region. So here's your region. Well, you have to draw the circle. So this is a circle, radius 1, but inside that. So here's your region. Here's your circle. And then up to the surface. So this is your surface. Somewhat complicated question. Okay, so to do that calculation then, first we want to define our function. Okay, and then we're going to put it into our radical. So to integrate over that surface this would take some work. All right, so let me go back to the surface integral. So here's the evaluation formula we're going to use. So D is that projection down. So here's your D in the XY plane, like that. So you're going to integrate over this region up to the surface. So this derivation that I did above here basically shows how that works. Okay, and then you can get rid of this. This has nothing to do with you guys. Okay. All right, so try this. This all works out somewhat nice. Okay, I won't spend time on this, so try this. See if you can get a value. This gets down to something you'd have to use a reduction formula or something. You just do this. Okay. So now I'm going to kind of go away from the sections that we're covering and just talk about, first we got to define orientation of a surface. Basically, it's you can orient it up or down, but not both, which I'll talk about. Okay, we'll define all that. We're going to define flux, flux of an integral. We're going to apply flux concept to what's called Stokes' theorem, and then apply the concept to the divergence theorem, and then that's it. We'll come back and do those.